Ok, vou recomeçar então. Vou recomeçar. So we are considering cocycles of this form. xv goes to f of x, ax of v, where where M is the space of sequences in GL2. F from M to M is the shift map. And A is locally constant. More precisely, it's just the projection to the zeroth coordinate. So that takes any sequence and maps to the zeroth, the value of the sequence in the zeroth coordinate. And then we consider measures, probability measures, nu k in GL2. All of these measures in the space of matrices are assumed to be compactly supported. And we assume that the sequence nu k converges to some probability measure nu in the following sense. in the sense that nu k converges to nu in the weak star topology. That's the first condition. And the second condition is that given any epsilon, it's a kind of convergence in Hausdorff topology as well. Given any epsilon, the support of nu k is contained in the ball of radius epsilon around the support of nu for every large k. And then what we want to prove is that the Lyapunov exponents associated to the nu case converge to the Lyapunov exponents associated to nu. And so we want to prove that lambda plus nu k converges to lambda plus of nu, and then there's a completely dual argument to prove convergence for lambda minus. So what we did last time was to reduce to the following standing assumptions. First of all, that lambda minus of nu is strictly smaller than lambda plus of nu. So first condition, because otherwise continuity is automatic. And then the other step that we already did was to consider stationary measures for nu k eta k such that they realize the Lyapunov exponent for nu k, namely that this is equal to the integral of phi d nu k times eta k trying to keep the notation consistent. For each nu k, we consider the Bernoulli measure, nu k to the z. And so this just means the integral of log alpha of v divided by v, integrated with respect to nu k of alpha and eta k of v. Okay, this is just what this integral means. So we take stationary measures that realize the largest Lyapunov exponents, then take eta to be an accumulation point or a limit of eta k. This is up to considering a subsequence. Okay. then the lambda plus of nu k converges to the integral because of the expression d phi d mu times eta, which is again the integral of log alpha v over v d nu alpha d eta v. And we may suppose, it's the other condition, that we may suppose second condition, we may suppose that this integral is less than lambda plus of mu. The reason we may suppose this is that otherwise they are equal, and if they are equal, that means we have obtained continuity. Okay, so in what follows, the rest of the proof is A plus B leads to a contradiction. Okay, so we may suppose this, but if we assume this, we get a contradiction. Therefore, we must have equality here, and so that proves this statement. Okay? So what I did last time on the way to obtaining a contradiction was to prove that A plus B implies that there exists some subspace, some line in PR2, such that there are several things. First of all, this line is invariant. And this can be restated. If you think that mu is just nu to the z, this really means the same thing as saying that alpha L equals L for nu almost every alpha. And this is just another way of saying the same thing. This is the same as saying that alpha L is equal L for every alpha in the support of nu. Okay, so this is first property. The other property that interests us is that L is an atom for the stationary measure nu, eta. And finally, L is equal to Vx2, which means that the limit 1 over n log of a n x v is less than lambda plus if v is in L, and this equal to lambda plus if v is not in L. Okay, this is where we stopped last time. That is 3 properties. The main thing here being the fact that, this was observed, it's quite obvious from the statement that L is equal to Vx2, but the point is that Vx2 in general depends on X, and this is one subspace, one is fixed, is constant, independent of X. Okay. So the rest of the proof is to go from here to contradiction. That's what we are going to do. Okay. So what I kind of announced is that I want to prove that we cannot obtain atoms as for stationary measures that come as limits of stationary measures for nearby co-cycles. Measures that are obtained in this way cannot have atoms of this type, at least. And to explain what I mean by this type, I have to introduce the following notion. So we say that a point V in projective space, and this part of the argument will be in any dimension, is expanding if well, first of all, I have to say what I mean by an invariant point is invariant if AX of V is equal to V for mu almost every X. And again, if you want, you can write this in this language here. This is the same as saying that alpha of V is equal to V for every alpha in the support of nu. Okay, so a point is invariant. A point in projective space is invariant if it represents a line that is invariant by almost all of the matrices. Okay, then we say that V is expanding if there exists a number C such that the logarithm of the derivative of AX of A, what is the notation? The beta V, I have to explain this, is the AX V dot d mu of X is positive for every V dot in the orthogonal complement of V. I have to explain this. There's some notation that has to be defined. So it goes like this. It's a very simple geometric notion, but it has to be explained. So we have, this is a representation of projective space. P, R, D. And we have a point in projective space that, which is just the point represented by, it's the direction of V. And this point is, by assumption, invariant on all the matrices. For each A of X, this is a linear map. This is a map from RD to RD. But I can look at this as a map from projective space to projective space. Right? Just projective action of this matrix. And the point V, this point, bracket V, is a fixed point. So I want to say that this fixed point is a repeller. That's what I want to say. So how do I do that? I consider any tangent vector here, any tangent vector, V dot, to projective space. So V dot is an element of, this is very complicated to write, the tangent space to projective space at the point V. Okay? And I want to say that when I look at the derivative of this map, it tends to grow. It tends to be bigger than 1. Now, first thing, this is very complicated to write, but it's very easy to see that the tangent space at projective space to a certain line can be identified with the orthogonal complement of the vector. Just think of the sphere. Okay. Okay. This is a line, and this is any vector that represents this line. Okay. So this is just, I'm just simplifying notations here. Instead of writing the tangent space, I will just say the orthogonal complement. Now I have the problem of giving a sense to the derivative. So I'm talking about this map. Okay, this is a smooth map. This is a smooth map in projective space, and so it has a derivative. Okay, and it's nice to know what the derivative is, and I'm going to tell you. And just leave the formula as an exercise. So if I have a linear map alpha, just a linear map, and I look at the action of this linear map in projective space, this is a calculation that you should do at least once in your lives. So consider alpha from projective space to projective space. And let's suppose, just to simplify the formula, that I have a fixed point. So that this V is a fixed point. So the derivative of alpha at this fixed point is a map from the tangent space here to the tangent space there. It's a linear map from the tangent space at this point to itself. Okay? Of course, if the point is not fixed, then you have something slightly more general from a fixed point at V to the fixed point at alpha V. And this can be calculated given given any v dot in tangent space, I can tell you what the derivative is. It is the you divide by alpha v, and then here you take the projection of alpha of v dot on the direction of alpha v. So this expression there, projection of u w, means the projection, the orthogonal projection of u to the orthogonal complement of w. Okay? So what I'm telling you is how you take derivatives of linear maps, of projective maps. You do it like this. And you can draw a cartoon of what I'm saying here. This is projective space here. You have your vector v, and how do you calculate the derivative? Well, for any tangent vector v dot, you just take its image under the linear map, which is something like this. Okay. Then you project that to the orthogonal of alpha v. In this case, alpha v is v. So you project this vector to the orthogonal to the tangent space orthogonally. So that would give something like this. Here's what you get, the projection. This is this. And then you divide by the norm of alpha v. Okay? Exercise, check this. Dimensions are fine. You are in dimension d, so projective space is a d minus 1 manifold. The tangent space is just your orthogonal complement, so it's d minus 1. And when you take any vector on that hyperplane, you look at its image, that's a vector, and you project to the hyperplane at the image. Okay. Any questions? I'm not going to use very much this formula, but, well, it's a nice formula, and it's nice that you can do things explicitly once in a while. Okay? So what I wrote there is, what I wrote here, I have a problem with notation, is the derivative of ax from projective space to itself at the point bracket v and in the direction of v dot. Okay, I've tried to keep the notation not too complicated. There are too many variables. Okay, so what is the condition saying? That for any direction that you look at, so for any v dot, when you calculate the derivative and you take the logarithm, on average, the logarithm is positive. Okay? So on average, in that direction, arbitrary direction, your matrices tend to expand along the tangent to the projective space. Okay, so this we sometimes call a probabilistic repeller. You have to keep in mind that when you have one dynamical system, you can define a tractor or repeller with respect to this dynamical system. Yes? Yeah, you're absolutely right. If I multiply v dot by some constant, I can, yeah, so this with norm 1. For every norm 1, for any unit, okay, we want the constant to be the same for all of the v dots, and that, and for that I have to normalize the v dots. Yes, thank you. So I'm saying that in any direction you look at, some of the matrices may expand that direction, others may contract, but for every direction, on average, they expand. The derivative is an expansion in that direction. Okay? And that we call, as I said, a probabilistic repeller. Okay, I'm going to tell you what is the expanding point we are interested in. Well, I already found here an invariant point. L is invariant. You see, this really means that L is an invariant point. And what I'm going to do next is to prove a lemma which allows us to show that because of condition C, L is also an expanding point. So, proposition. Suppose you have a point in projective space. So it's an invariant point. And suppose that there exists numbers alpha A and B such that such that the limit 1 over n log a n x v is less or equal than a if now I have a problem with notation here. Let's call this L. If V is in L, and it's bigger or equal than B if V is not in L. Okay, So this is the case for the subspace that we found in this proposition. So I'm going to apply that statement there to this subspace here. A and B being given here. So suppose then, I didn't finish the statement, then L is an expanding point. Let me draw a picture. I want to convince you that the statement is more or less obvious before I spend some time proving it. So here is projective space. And here is the line L. This is L. Okay? This is, and then I take a vector, tangent vector v dot. So how do I expect these vectors to behave? I mean, how do I expect them to evolve under iteration? I can take a vector here inside V, inside L. So take V inside L. And given V dot, I can also find, I can decompose V dot as the sum of V and some W that's not what I want to say. I want to say that I can think of V dot. V dot is a vector which is orthogonal to V. Okay? Now, what happens when I iterate? Let's try to imagine what happens when we iterate this picture by any of these matrices. V may grow or not, but in any event, we know that V remains in the same direction because L is invariant. Okay? Let's suppose that V decreases because vectors in the direction of L tend to not grow very much. So typically, one possible situation is that A of x applied to V is smaller than V. Okay? Now, what about V dot? V dot is orthogonal. It's definitely not in L, so it tends to grow. So I'm going to draw the image of V dot as a very big vector. Perhaps not orthogonal. Okay? And I want to understand from that what is the derivative I want to understand from that whether this derivative is big or small. Okay? Now, what is the derivative? Is the projection, the orthogonal projection of Ax V dot. I erase the formula. You have to believe me that I'm saying exactly the same thing. So I take this vector here a very big vector, and I have to project it. I'm going to draw it here to make it easier for me to project it. So this is AX of V dot. I have to take this vector and to project it to the orthogonal complement of to this, to V orthogonal, right? So I have to project this orthogonally so I expect, unless something very bad went on, and the angle, you know, this is usually not orthogonal anymore. It could be very much a line along L, but unless that happens, I expect this projection to be very big. Okay, but the projection is not the derivative yet. The derivative, to calculate the derivative, I have to divide by AX of V. Okay, which is small. Okay, so I have a big vector growing at this rate B. I have to project it, which could make it smaller. That's true. This projection could make it smaller. And then I have to divide by the norm of this vector, which is a small number. So this is probably going to be large. And so the logarithm is probably going to be positive. Okay. And that's why the proposition is true. Well, this is an explanation, but I want to give you an example that probably is much more illuminating than what I just said. Let's look at this matrix from R2 to R2. The matrix 2, 0, 0, 1 half. Just one matrix. Okay. It has two fixed points in projective space, the eigenspaces. This is a fixed point, L1, and this is another fixed point, L2. Now, if you look at the action of A in projective space, so you have these two fixed points. One of them is an attractor, and the other one is a repeller. Which one is the attractor and which one is the repeller? Okay, which one is the attractor? L1 is the attractor, right? If you take any line and you iterate it, the horizontal component grows, the vertical component decreases, and this is the attractor and this is the repeller. Okay. The dynamics is a north pole, south pole dynamics, and the repeller is precisely the subspace where your matrix is contracting. Okay? Being contracting, I mean this kind of property, that vectors inside the subspace contract more than vectors outside, means, when you look in projective space, means that you have a repeller. Okay? And the explanation why this proposition is true is exactly that. That kind of, we have that kind of behavior, except that it's, I mean, there's this is for mu almost every x. It's a more complicated situation, but it's the same kind of behave. Okay? So let me maybe give an outline of the proof. The proof is not very interesting. Once you know why it's true, it's not very interesting. Yeah, maybe I want to write this as follows. Again, using the expression for that mu is a Bernoulli measure. I will write this as log of d alpha v at v dot log of the absolute value. This is norm. Log of the norm d nu of alpha. Okay, so let me. The proof will be essentially this picture here. We have to be careful about the angle when we project, but otherwise that's the proof. Okay, so this condition here says that well, yeah, I managed to use a section that doesn't exist in the book. That's why I'm a little bit puzzled. Okay, so proof. The you take your v in L, so v dot in the complement, and then we have these that the limits 1 over n, so that the norm a n x v is less than the limit 1 over n log of a n x v is less or equal than A, because of this condition here. And then the limit 1 over n log of ANX V dot is bigger or equal than B, because V dot is outside. And this implies that the limit 1 over n log of the projection ANX V dot is also at least B, and that's the part that's not entirely obvious, but let me try to convince you that it's true. It goes like this. By assumption, our direction L is invariant. This direction is invariant. So when I apply A and X, this is preserved. Now I'm taking another vector, V dot, which is outside. And, well, we already have the Oscilladets theorem, so we can project the V dots into the other subspaces in the Oscilladets decomposition along the direction of L. So what I'm saying is that we can consider the component, I don't know what to call it, W, the component W of V dots in the direction of the other subspaces, T. This is the sum of the other Oscilladets subspaces, because L is one such subspace since it's invariant. Okay. Now, when we iterate the it's easier to pretend that W and V dot are the same. When we iterate W, it may happen that the angle, this is ANX of W, it may happen that the angle between ANX of W and L goes to 0. This angle may go to 0. However, it will go to 0 sub-exponentially, and that's part of the Oscilladets theorem. Oscilladets says that the angle between between ANX of W and L goes to 0 sub-exponentially. Means that at any point, at any moment, it is bounded below by something which is an exponential with small exponents. Okay? So, when you take this vector and you project to the orthogonal of V, so this implies that the projection of W to the orthogonal of V, to L orthogonal, is at least the norm is bigger or equal than the norm of ANXW multiplied by the sinus or the cosinus of this angle, and so multiplied by e to the minus n w, n epsilon. So what I said is, if this vector remains orthogonal, then this would be telling us that it's growing very fast. And that would be okay. We have a problem that the angle may go to 0, but I'm saying that the problem is not very serious because the angle cannot go to 0 very quickly. So this w, so this proves, this implies that the limit 1 over n log of anx w is bigger or equal than the limit anx w sorry, the projection. Minus epsilon. And epsilon is arbitrary. Epsilon is completely arbitrary. So at the end, you can make epsilon go to 0. Okay. Then there's the difference between w and v dot that we have to look at, but that's irrelevant because the difference w minus v dot by construction is in L, and so it grows very slowly. It grows slowly. It doesn't change. It doesn't change the rate of growth of either. And so where you have w, you can now write v dot without changing. This grows slower than a, and so it doesn't change the rate of growth of these vectors. I'm not sure this is entirely clear, but really everything I'm saying is that we know that the angle cannot go to 0 very fast, so the projection doesn't decrease the norm very much. So, and then that it follows that dax v dot limit 1 over n log of this norm. It's just the difference between these two. It's this minus this. It's just the difference is bigger or equal than b minus a. This is a. Okay. Then what? That's not what we want. What we want is this. Or this. What we want is this. Now, this is positive, right? This is positive. In fact, we can take c, the constant c, something like b minus a over 3. And then this is bigger than c. Bigger than 3c. So we have a sequence of functions. namely 1 over n log, etc., such that the limit is bigger than 3c. We want to take the integral and say that this is bigger than c. Well, we cannot. This is something that happens in the limit when n is very big. So I have to go back to my definition and adjust it. If there exists c and n such that these holds for n. Okay. So the condition of being expanding says that if I take some sufficiently large iterate, then on average it expands the tangent space in every direction. But I have to take a sufficiently large iterate. And now really there's not much else to do. If I have a limit, if I have a sequence of functions whose integrals converge to 3c, of something bigger than 3c, then this implies that the integral is bigger than c for n sufficiently large. And this is just the bounded convergence theorem. Bounded convergence, or yeah, by bounded convergence. Okay. The bounded convergence theorem says that if the integral of the limit is the limit of the integrals, the limit of the integrals is the integral of the limit. If the sequence is bounded. This sequence here is bounded because a of x is bounded. The norm of a of x is bounded because we suppose that nu has compact support. All our matrices with full measure is bounded almost everywhere. Okay. And then here I have the nth iterate, but I'm also dividing by n, so this sequence is bounded. Yeah, okay. I don't want to say more about the proof. It's just, there's nothing, really not much more than that. To say that the that if you have, so the moral is that if you have a subspace like this, it constitutes a repelling fixed point, a probabilistic repelling fixed point for the action in projective space. Okay. And what I'm going to prove, so what we will prove is that if L is an expanding point, then it cannot be an atom for a measure eta, which is a limit of a stationary measure that is a limit of stationary measures for nearby cocycles. So A means L is invariant. C implies that L is expanding. And what we are going to prove is that if L is expanding, then it cannot satisfy B. That's the logic of the argument. Okay? There's a moral motivation here. You have a point L in projective space, a repelling point. So the other nearby points tend to move away from this. And this, what I'm going to do next is to show that that kind of bad popularity of L is also reflected in nearby stationary measures, so that they cannot accumulate mass on L. Right? In a sense, that picture was the motivation for okay, but for that I have to open a different chapter. So the program is for the rest of the proof is what I wrote there. Expanding points, probabilistic repellers cannot be atoms of stationary measures that come from nearby stationary measures. But to prove that, I need to introduce some ideas. So I'm going to speak a little bit about couplings and energy. Okay, so I'm going to consider, so P is some compact metric space. In our case, it will be PRD. And given measures, eta 1 and eta 2 in P, we call a coupling of the two is any measure C in the product so I have this product P times P, and a coupling of the two measures is any measure in the product such that pi 1 star of C is eta 1 and pi star 2 of C is eta 2. So is any measure that when you project it to the first coordinate you get eta 1, when you project it to the second coordinate you get eta 2. Okay. Now, do couplings exist? I'm going to give examples, but do couplings exist? Well, it's clear that there is a restriction. Xi of P times P, the total mass of Xi, the measure of the space, is equal to eta 1 of P, because when you project, the total mass remains the same. By definition of what this projection is, the measure of P for eta 1 is equal to the measure of P times P for Xi. Okay, so, and of course, for the same reason, this is equal to eta 2 of P. So we need to assume that eta 1 and eta 2 have the same mass. So we need to assume assume that the mass of eta 1 is equal to the mass of eta 2, where I call mass of a measure the measure of the whole space. Okay, so this is necessary if I want the notion to make sense. On the other hand, if this condition is true, I'm not assuming that the etas are probabilities. Of course, if they are probabilities, that's true. But then, if this is true, then we can take there's at least one coupling that is very easy to find, which is just the product. Then take C equals eta 1 times eta 2. Okay. Well, actually, it's not okay. It's not correct. Suppose eta 1 has total mass 1/2, and eta 2 has total mass 1/2. Then the product has total mass 1/4. So this is not correct. You have to divide by the mass. Then it's okay. Of course, when we are dealing with probabilities, the product of a probability by another probability is a probability. Okay? So this is one example of coupling, also called a trivial coupling. Another example. Another example. Take eta 1 equals eta 2. Now, when the two measures are the same, we speak of self-coupling. So we have the same measure on the two factors. And now I'm going to produce a different coupling, just to give you an idea that the notion of coupling is very flexible. I'm going to produce a different coupling, in a sense, the most different possible from the trivial one, at the other extreme. So the coupling will be defined like this. This is the diagonal, and in the product space, and I define Xi of E times the diagonal. Xi of E. I want to put the measure totally on top of the diagonal, and to be just a copy of eta on either coordinates. So Xi of E of any domain E is just the same as Xi of E intersected with delta, with the diagonal, and by definition is the measure of the projection of E intersection. So projection of pi 1, the measure of pi 1 of E intersected with delta. Okay. This is my definition of take C of E equals pi 1 or pi 2, because it doesn't make any difference. When you project the intersection with the diagonal, what you get here is exactly the same thing as you get here. Okay, if you want a different formula saying exactly the same thing, is the measure of the set of X in P such that the pair XX belongs to E. Maybe it's easier to understand this one. So I said that this is also a coupling. When you project, you get exactly eta. And in a sense is as separate as possible from this. This is the coupling by multiplication, by product. It's a coupling where eta 1 and eta 2 are essentially independent. And here I'm coupling them very strongly, that so whenever one moves, the other one has to move as well. Anyway, it's just another example of a coupling. And we will see other constructions, more complicated, more interesting constructions of couplings. Now, I'm going to, this is the notion of coupling. Now I'm going to talk about energy. So, given delta and a measure C in the product, we define the delta energy of C to be the 1 over the distance from X to Y to the power delta, and then we integrate with respect to C. So, why is this called energy? Because whoever thought of this, imagine that we are putting on P electrons and particles with the same charge. And particles with the same charge don't like each other, so they try to move away. So in order to keep them in the same place, you have to spend some energy. And the energy depends on the distance. In real life, electromagnetism, the energy is 1 over the distance. We generalize that by putting an exponent here. Okay, potential energy associated to an electric field is 1 over the distance between the points. And then, in fact, you have some distribution of mass of these electrons, and you take the average over all the distances. You average out all the energies, all the associated to each one of them. So that's, I guess, how you come to this this expression. If you have a particle in the diagonal, then it's infinity. I will discuss when this energy is infinite. What you said is morally true, but not quite true. I will fix it. Okay? It's a bit surprising that it's not true as such, but okay. So this is the energy, the delta energy of C. Now I'm going to define, given a measure eta in P, we define its delta energy with small e as follows. It's the, I'm sorry, what you said is correct, but I'm going to say something which is more deeper and has to do with this one. When is this finite? So the energy of a measure, now I'm talking of a measure in P, is the infimum of the energies of all its couplings, self-coupling. So this is the delta energy of eta. Okay. Now, of course, as any definition that is given, so the idea is that if you want to calculate the energy of a measure, you are going to look for the most economical coupling you can produce with that, for that measure. Maybe I'll give you an example. A simple example. Suppose that P is the interval 0, 1, and eta is 1/3 delta Dirac at 0 plus 1/3 delta Dirac at 1/2 plus 1/3 delta Dirac at 1. Okay, and I would like to say something intelligent about the energy, the delta energy of this measure. The first attempt we would do would be to take Xi, the coupling. I mean, 10 minutes ago we didn't know what a coupling is, so we don't have many examples to play with. Let's play with the product. Eta times eta. Okay, so that would mean that I'm going to consider a measure with 9 atoms, that's Xi, a measure with 9 atoms located on these 9 points. Okay, so what is the energy of this Xi? Well, that's easy to see, right? We have to calculate the integral of 1 over the distance with respect to Xi, and Xi is formed by 9 Dirac masses on these 9 points. For example, there's an atom with mass 1/9 here, and here on the diagonal the distance from x to y is 0. So just, that's what Dimitri said. Here the function is infinity, and the point has some weight, so the integral is infinite. Okay? If you have an atom for Xi on the diagonal, then you're lost. Then your energy is infinite. You have 2 electrons in the same place. That requires infinite energy to happen. Okay? But this, of course, doesn't say anything about the energy of eta. I'm going to try to be a little bit more clever and find a different coupling that that could give finite energy. I mean, I only have to put a measure on the square in such a way that it projects on 3 Dirac masses here and 3 Dirac masses here. And one thing that I could do is to try to keep Xi symmetric. We talk of symmetric self-coupling. Symmetric self-coupling, or symmetric measure. Symmetric measure in P times P. Symmetric means invariant under the symmetry, under the map that sends xy into yx. A measure that is invariant when you do this. Of course, the product is invariant, is symmetric. That one that I put, you see, from the point of view of energy, this is the worst kind of coupling. That's precisely what you want to avoid, because this, you're putting all your mass in the region where the function is infinite. So I'm going to construct another coupling for eta, and I'm going to do that in a clever way, avoiding the problem here. The problem here were the atoms on the diagonal. So I'm going to avoid them. And once I think like that, it's more or less clear what I have to do. I want a measure that projects only on 0, 1/2, and 1. And I will construct it symmetric so that I don't have to worry about the other projection. And I don't want to use this point. This is out, and this is out. Since I want the measure to project on these 3 points, I cannot use this region either, or this by symmetry. So I have to use the other 1, 2, 3, 4, 5, 6 points that are left. So here's what I'm going to do. I'm going to put a mass of 1/6 here and 1/6 here. Now wait. If I put 1/6 here, I have to put 1/6 here as well. Okay? So here I will take atoms, this is by symmetry, atoms with mass 1/6. Also mass 1/6 here and here. And then 1/6 here and 1/6 there. Okay? So it's still Dirac measures, but the weights I'm choosing, and 0, 0, 0, and 0. So Xi now is 1/6 times Dirac on 1/2 0 plus Dirac on 1 0 plus Dirac on 0 1/2 plus Dirac on 0 1 plus Dirac on 1 0 0 yeah, 0 1/2 1 1/2 then 0 1 and then 1 1. That's my Xi. And it's clear that when I project here, I get 1/6 plus 1/6 mass on 0, the projection. When I project here, I get 1/3, and also get 1/3. So this is a symmetric self-coupling of at another symmetric self-coupling of eta. Everyone agrees? And it's clear that the energy of this Xi is finite. And so the energy of eta is finite. Okay, when you integrate now, so what is the energy? What is the energy of Xi? What is the energy of Xi? Let's calculate it. The energy of this second coupling is 1/6 times the distance from x to y. The distance from x to y is 1/2. 1/2 to the minus delta. Plus 1/6 distance from x to y here. X is 0, y is 1. Here, 1/6, 1/2 to the minus delta. Here, 1/6, 1/2 to the minus delta. 1/6 1 to the minus delta, and finally 1/6, 1/2 to the minus delta. And this was wrong. Something here was wrong. 1, 0 1/2, 0, 1, 1, 1/2. 0, 1, and 0, 1/2. And 1/2, 1. Okay, I'm referring to these 6 points here. Okay, so the energy here for this coupling is 1, 2, 3, 4, 6. 4, 6, 2 to the delta, plus 2, 6, plus 2, 6. So it's finite. Okay? Esse aqui. 0,1. Vamos ver. Esse é 1 meio 0, né? Esse é o 1, 0. Depois vem o 0, 1 meio. E esse aqui. Vem o... Vem o 1, 1 meio. Ok. Depois vem o 0, 1. E depois vem um meio 1. Ok? Então isso aqui ilustra um pouco o tipo de truque que a gente pode usar com acoplamentos. Sorry. This illustrates the kind of trick we can use with couplings, which is that sometimes we can move the measure around the square without changing the projections. And we were very successful here in taking mass from these dangerous atoms and put them in other atoms. Observe that, I mean, there's a counterpart to what Dimitri said. If Xi has an atom in the diagonal, then the energy is infinite. But there's another observation which is just as useful. If the support of Xi is disjoint from the diagonal, then the energy is necessarily finite. Right? If the support is far away from the diagonal, then the function that we are integrating is bounded, and so the energy is finite. Okay, and that's precisely what I did here. I found another coupling which is supported, whose support doesn't intersect the diagonal. Okay, so let me, we don't have much time left, but let me state some things about couplings and energy that we are going to prove tomorrow. first of all, so properties. The function that associates to, I will keep the notation, eta for measures in one factor and xi for measures in the product. The function that associates to each xi its energy is lower semi-continuous. Let me prove that it is continuous, which it is not, and then it will be, I think, will be clear why we get semi-continuity. I'm talking of continuity with respect to weak star topology. The function 1 over the distance is a continuous function. So, just by definition of weak star topology, this should depend continuously on the measure xi. Of course, there's a little problem that 1 over the distance is not defined on the diagonal. 1 over the distance is continuous in its domain, but it's not bounded. So the proof of 1 is to take into consideration the special role of the diagonal, work around the diagonal. But we'll come back to that next time. Consequently, for any eta, there exists some coupling xi such that the energy of eta is realized by the energy of xi. Okay, so the energy of eta, I erased it, was defined as the infimum. I'm saying that the infimum is also always realized. So for any delta and any epsilon, and any, for any eta and any delta, there exists some coupling that realizes, that is the most efficient coupling, the coupling with the smallest possible energy. And we call this an optimal. Well, no, we don't call this an optimal. 3, in fact, we may take xi, this xi, to be symmetric. So what I'm saying here is that the energy of any measure is realized by some coupling, and we may choose that coupling to be symmetric. Okay? And then we call it optimal. Delta optimal coupling. I'm saying delta optimal to stress that it depends on delta. So this is saying that if you choose a distribution of charge here, energy, nature will find a way to minimize the energy, to have a distribution of mass here that minimizes the energy, and that distribution can be chosen to be symmetric. So why are we talking about couplings and about energy? What does this have to do with our situation? And the answer is this lemma that I'm going to state. Remember that we want to prove that an expanding point, etc., cannot be an atom. So how do you prove that there are no atoms? What is the tool? And energy is that tool through the following lemma. if the energy of eta is finite, then you see, I found an example here of a measure whose energy is finite, and yet it's a very unpleasant measure. It's just Dirac masses. It has atoms. So the fact that the energy, it's not like here. If we have an atom in the diagonal, then automatically the energy is infinite. But it's not the same thing. This is much more subtle. Eta may have atoms and still have finite energy. However, if the energy is finite, then the mass of any atom is at most 1/2 of the total mass. So when the teacher chose a measure with 3 atoms, each one with 1/3, he knew that he couldn't do it with 1/2. For every x. Okay, so I could do it with 1/3, with having atoms with 1/3 of the total mass, but I couldn't do it with 2/3, for example. More interesting, if the mass of every point is strictly less than half the total mass, then the energy is finite. Okay? So this lemma, if it's smaller for every x, then the energy is finite. So how are we going to prove this? This is an interesting proof. It cannot be just by taking the product coupling. Because if your measure eta has atoms, say atoms with mass 1/3 or whatever, if you multiply, the product has atoms on the diagonal, and so the product will get infinite energy. We will have to do something similar to what I did here when I shuffled mass a little bit around. But anyway, through these two properties, we can use the energy to detect the presence of atoms. And please keep in mind that I'm not assuming the etas to be probabilities. This is not about atoms that have mass less than 1/2 or bigger than 1/2. If you have any atom, anyone, if you look a very small neighborhood and you look at the measure restricted on a very small neighborhood, then this atom will have more than 1/2 of the total mass. So by focusing on the neighborhood of every point, you can actually use this statement to identify any atom. And that's why it's so useful. Okay, but I don't want to start that right now. We will do that tomorrow.